Welcome back, and this is the next in the series of videos looking at the inorganic chemistry applications. And we're going to start off by looking at the need for alternative fuels. I'm going to start on page 6. So obviously the need for alternative fuels is very important, especially to combat global warming. I'm not going to spend too long on these questions. They are also available in your alkane notes when we looked at alternative fuels in the lower 6th year. So, governments are increasingly concerned about our use of fossil fuels for two reasons. Firstly, the combustion of fossil fuels leads to the production of greenhouse gases and hence global warming. If you also burn fossil fuels which have sulfur in them, you're also going to get acid rain. And secondly, they are a finite resource. So a lot of research is going into alternative chemical energy sources such as wind, solar, nuclear, and so on. You need to have a very basic understanding of the greenhouse effect, in the fact that the greenhouse gases act as a blanket and they prevent the energy from being re-radiated back out into space. So the energy coming in is different from the energy going out. So carbon dioxide is one of the most important greenhouse gases. It causes global warming, which can cause the glaciers to melt, sea levels to rise. There's also more energy in the atmosphere itself, which means that the atmosphere can hold more moisture, which leads to more violent storms and so on. It also changes the pH of the oceans, and that causes things like coral bleaching. Biofuels are sometimes described as carbon neutral. That's because they only release back the original CO2 that they absorbed via photosynthesis. This is not exactly true, as biofuels still need to be processed, harvested, and so on, and that is all energy intensive and often releases more CO2. Sustainable development basically means not using up non-renewable or finite resources, and also trying to produce the minimum amount of waste that could then have an effect on the environment. So alkanes and other hydrocarbons burn to produce carbon dioxide and water. Now, if there is incomplete combustion, you would also get some carbon monoxide and just some carbon, otherwise known as soot. But remember, you would always get water. So complete combustion, carbon dioxide and water. Incomplete combustion, either carbon monoxide and or carbon, but always water. So propane, C3H8 and oxygen burn to form carbon dioxide and water, because this is complete combustion. I do need to make sure it balances. So I've got 3 CO2, 4 H2O, and therefore 5 oxygens. Again, talking back to limited availability of oxygen, if I take my propane and I burn it again, but I'm limiting my supply of oxygen this time, I can produce carbon as well as carbon dioxide and water. So I know that those are my products. I just need to balance it again. So I'm going to have 2 carbon dioxides this time, still got 4 waters, and that gives me 4 oxygens. I can limit the oxygen still further to produce carbon monoxide, carbon dioxide and water, CO, CO2 and H2O. Again, I'm always going to make my 4 waters. This time I'm going to have 2 CO, and again I've limited it to 4 oxygens. Other pollutants that are associated with burning hydrocarbons are sulfur dioxide, nitrogen dioxide, and obviously unburnt hydrocarbons. So sulfur dioxide, first of all, the sulfur can react with oxygen to form sulfur dioxide, SO2. That sulfur dioxide can react to form sulfur trioxide, 2 plus half, and O2 goes to sulfur trioxide. Both of those could then react with water to produce acids, sulfuric acid predominantly, and that is what we mean by acid rain. Last but not least, we have nitrogen dioxide. Now, though the nitrogen dioxide is not actually coming from the fuel itself, it's an atmospheric reaction, and it only happens at the very high temperatures you get in a car engine. And at those temperatures, the nitrogen can actually react with the oxygen to make the NOxes, NOx, and that could be NO2 or NO. Likewise, like the sulfur, the oxides are acidic, and they can react with water to form acids. So we get NO2, nitrogen dioxide, reacting with the water in the atmosphere to make HNO2 nitrous and nitric HNO3 acids. Again, we need to balance it. I need 2 there. So skipping over the practical demonstrations on the previous page, we're now looking at homogeneous catalysts. And if you remember, a homogeneous catalyst is one which is in the same phase as the reactants. Quite often we find this in biological systems rather than industrial systems. In industry, remember, we'd always rather use a heterogeneous catalyst because it's much easier to separate. However, in biochemistry, it's quite often homogeneous catalysts. One example that you should be familiar with is the catalytic ability of the ion Fe2+ and Fe3+ to catalyze the iodide peroxydisulfate reaction. This iodide peroxydisulfate tends to be a very slow reaction. It has a very high activation energy, and the reason for that is that you're trying to react 2 negative ions together. So that's why this reaction is very slow. So we're going to catalyze this either starting with Fe2+ or with Fe3+. And in the same way as the sulfur dioxide reaction with oxygen, the peroxydisulfate and the iodide never actually react together. They react with the ion species rather than each other. Hence the lower activation energy and the faster reaction. The reactions, however, still need to balance. Well, the sulfur is changing by 2, so I need 2 ions to balance it. So there's 2 Fe2+ going to 2 Fe3+, and likewise here, each iodide is changing by 1, but there are 2 of them, so I need the 2 Fe3+ to 2+ to balance. Now I just want to work out whether or not these reactions are feasible, and I can do that by using the E cell values. So I know that S2O8 being converted into SO4 has a value of plus 2.01, so that's plus 2.01. The Fe2+ is going to Fe3+, so this is the reverse of this reaction, so that is minus 0.77, but that still comes out as a positive number, plus 1.24 volts. So that reaction is feasible. Looking at the second reaction, where I'm going from iodide to iodine, so that's the reverse of this equation, so that would be minus 0.54. But the Fe3 is now going to Fe2. Fe3 to Fe2 is a positive value, plus 0.77. So again, I get 0.23 as positive, and that's volts. So that again is feasible. Another catalytic process you need to be aware of is what we call autocatalyst. Again, you've got your C2O4 2- ion trying to react with your manganate MnO4-. This again is a slow reaction for the same reason as previously. We have these 2 negative ions which we're trying to react together, so therefore the activation energy is going to be very high. So in this case, it is the Mn2+ ions which are acting as the catalyst. This is very easy to see on a rate of reaction graph. So if we look at a concentration time graph, and here I'm just measuring the concentration of the carbon dioxide as one of the products with respect to time. It's going to start very slowly as we have no Mn2+, and it's quite a slow reaction, but then as the Mn2+ is produced, this rate of reaction increases, and then obviously the amount of carbon dioxide levels off. So these kind of reactions are very easy to spot because of this very distinctive shape they have to a concentration time graph. In other words, they start off really slowly and then they accelerate. The rate of reaction significantly increases until you've got all of your carbon dioxide. So what you'd physically see is a little bit of fizzing at the start and then the fizzing becoming rapid as the reaction speeds up, and that purple colour fading. So we're moving on to look at complex metal ions' stability constants. So we know that some ligands are able to displace other ligands. So for example, with copper 2 ions complex with water molecules and the hexa-aqua ion, if you add an alternative ligand, such as 1,2-diaminoethane, that will displace the water ligands because the resulting complex is more stable. Another example of this is, again, the hexa-aqua ions reacting with the chloride ions to make the chloro complex. The chloro complex is more stable than the water complex, so the equilibrium position lies well over to the right-hand side. But this is still an equilibrium reaction, so we can still write our Kc expression for it in exactly the same way that we would have done anything else. So we have the concentration of the CuCl4 2- divided by the concentration of the hexa-aqua ion 6 2+, so that should have a 2+ on it, times by the chloride ions raised to the power 4. Okay, and that should have 2+ on it. Notice we don't include the water, and the reason we don't include the water in our Kc expression is again because it is a solvent. And remember, we don't include solvents in our Kc expression because their concentration doesn't change. We give this a special name. We call it K-stab for the stability constant. And the larger this stability constant, the more stable our complex is when compared to the hydrated ion. We can also bring entropy into the equation, and we can look at the entropic effects of changing the ligand. So again, if we do a ligand exchange reaction between the hexa-aqua ion and we add some of our 1,2-diaminoethane. Now here we've got enough of a carbon chain that the two nitrogens can bend round to come in at the correct bonding angles. So we have again our hexa-aqua copper ion, 6 water ligands surrounding my copper 2+, and again that is aqueous, and we're going to add the 1,2-diaminoethane. So I've got my NH2, I've got a CH2, CH2, NH2, and remember both of the nitrogens are available, so I can use both of those lone pairs, and I can make that into my complex. In this case, all of the water molecules are replaced by the aminoethane molecules, so we get copper, and remember this forms 2, so I only need 3 of these to make 6 ligands, or 6 dative covalent bonds, so I'm going to have 3 of those. Not changed any oxidation numbers, so I'm still 2+ aqueous, and I kicked out my 6 water molecules there, and obviously I need 3 there. So the entropy of the system, remember that's to do with the chemicals, so the entropy of the system increases, so it becomes more disordered. And the reason for that is you're going from 4 particles on this side. So I have 4 moles of reactant, or 4 particles of reactants. And they're changing into 7 moles. Better call that moles. A reactant to 7 moles of product. So there's an increase in the number of species. So I'm going from 4 species on this side to 7 species on this side. So there's an increase in entropy. If we take an even bigger ligand, such as EDTA, EDTA can actually form 6 dative covalents, because I can also use these 2 nitrogens here to form the last 2 dative covalent bonds. So in this case, I'm going from 2 particles to 7 particles. And again, that's a very high entropic effect. And therefore, the polydentate ligands are much more stable than biodentate or monodentate. And this is known as the chelate effect. And EDTA was used as a treatment for heavy metal poisoning because of this chelating effect. The EDTA would bind to the heavy metal and it would stop it from interfering with the cell biology.